Assalamu alaikum students. I hope you are doing well. Today we talk about gas gathering system. What is gas gathering? Basically, you need to have, example, if you are working on an offshore industry or even onshore also, you have different locations where you can get the gases. Okay, so it means like you have different wells, gas wells located at different locations, and now you need to transport those gases from different location to one particular location where the gas plant is located. Okay, where you will treat the gases further. So the basic idea of this process is that you need to collect the gas which is located at different gas wells. Okay, and then combine them at that particular location, or send them to that particular location where you can treat the gas. Okay, so you need to collect the gas at different gas wells, transport them through pipes, okay, to one particular place where the gas is being treated or handled or being treated further. Okay, so for example, in case of Oman, let's say that you have one gas well that is located in Nizwa, one is located in Ibri, one is located in Salala, and the plant that you have is in Muscat. So what you need to do, you need to take the gas from all these gas wells, transport them through pipeline to Muscat where the plant is located. Okay, you can further treat them at that particular region. So what we are trying to do with this particular session, how we can transport the gas through pipeline using Aspen HYSYS. Okay, this is what your idea, what the idea of the simulation is. So the problem that we have, the question that we are going to address in this one is, in this example, a gas gathering system is located on a varied terrains. Terrains means different wells. Is simulated using a steady state capabilities of HYSYS. So remember one thing, obviously when you talk about pipeline or talk about the gas transport, all these processes are basically dynamic in nature, but in Aspen HYSYS it is normal practice that we do the steady state first, and then when the steady state is solved, then we can move on to the dynamic simulation. But due to the limitation of this course, we are only focusing on the steady state part. We are not talking about the dynamic part yet. Okay, maybe later on, somewhere, if you need it, then we can talk about the dynamic part also. So the following figure, which is the next figure, shows the physical configuration of the system superimposed on a topographic map. The system consists of 4 wells. So we are working with the 4 wells distributed over an area of approximately 2.0 square kilometers. We have 4 different wells that is basically located at the area which is 2 square kilometers. Okay, so we have different wells, which is one well is one part of the this square kilometer area, and one well is other part of the square meter area, and the third and fourth also in different parts. So what we need to do, we need to combine all those areas. We need to transport the gases from all those wells to one particular place where we can treat them. Okay, so connected to a gas plant via a network of pipes. So we need to collect all this information, all these gases from the wells, 4 wells, transport them through a network of pipes to this gas plant. Okay, where we can treat them further. So on a topographic map, this is what is happening basically. If you look at here clearly, there are 4 gas wells. These are wells: well A, well B. Similarly, you have well C and well D. Okay, and these are the pipelines that is basically transporting well A gases from this part. This one is B, where it is transported the gases through this pipeline. Similarly, gas C, which is transported through here. Well D passes from here. Okay, now more thing that you need to understand, that this pipe that we talk about is named as branch 1, branch 2. Similarly, we have branch 3, we have branch 4, branch 3, then similarly we have branch 5, and we have branch 6 and branch 7, 6 and 7. Okay, so all these are branches basically, and all these branches are connected at different junctions. So this is junction number 1, this is junction number 2, we have junction number 3, Okay, so we have three different junctions. So just imagine this is as a mixer. Okay, so you have one coming from here, one is coming from here, is mixing at this point. So this is basically act as a junction, which is act as a mixer. Similarly, this one is coming from here and this one is coming from here. This is also act as a junction. Similarly, they will go like this, and here you can get the gases from here and you can get the gases from here. They are combined at this particular region, and this is another junction, which is another mixer. Okay, finally we have all the gases combined, and then we can send them to a plant. This is the gas plant where we can treat them further. Okay, so we have this particular area, which is 2 square kilometer area, and this square kilometer area we have 4 different wells. All these wells are producing some gases, and we need to transport those gases through those pipelines, adding them into a junction, different junction, and finally it reaches to a gas plant where we can treat them further. Okay, so similarly, there are a few more things that we need to assume here. First is that the composition of all these 4 wells, the composition of the gases that is present in the wells are same. Okay, this is something we are assuming. Obviously, it is not true practically, because if you are taking the gases from different gas wells, you might have some difference. Okay, but in this particular region, due to sake of simulation, due to make things easy, we are assuming that the composition of the 4 wells are same, which is mentioned here. So we have all these components, and plus we also have a hypothetical component, which is shown here. The information for hypothetical component is shown here. The molecular weight for hypothetical component is 122. The density of this hypothetical component is 47.41 pound per feet cube. This is the information for the hypothetical component. Because we have 4 different pipelines, means like if we have 4 different wells which is transported through 4 different pipelines, so we need to know the information regarding the temperature, pressure, and mole flow rate. So for gas well 1, which is coming from the pipe, you can say branch 1, they have the temperature which is mentioned here, the pressure mentioned here, and flow rate. Similarly for gas flow 2, 3, and 4, we have the temperature, pressure, and mole flow rate, which is shown here. This is something which is given to you. Similarly, some other information regarding the pipeline, because we are talking about the pipe, and pipe does have some length, some diameter, and they also have some elevation. Either if it is elevated or if it is not elevated, they have some information like this. So we need to provide this information. So for example, branch 1, which is pipe line 1, we have segments, 3 different segments, 1, 2, and 3 different parts of the pipeline. If you go back here, this one you can see here, this is branch 1, this is one segment, this is from here to here another segment, and from here to another here 3 segments. Similarly, well B, we have only one segment. Well C, we have also one segment. We have 2 and 3 segments. Similarly, well D, we have 1 and 2 segments. So in this way we can divide these pipelines based on their segments, okay, which is shown here, and information regarding those segments, the length, the elevation of the segment is mentioned here. And branch 2 have 1 segment, branch 3 have 3 segment, branch 4 have 1, branch 5 have 1, 6 have 2 segment, and 7 have 1. Okay, and similarly we have their elevation, which is shown here, their length and their elevation in meters, and their change in the elevation change meters is shown here. What else we need? We need to know what is the diameter of the pipe. So diameter, as you remember, we can represent the diameter of the pipe by the schedule number. And we also assume that all pipes are buried, okay, I mean buried in the ground. It is not hanging on the top of the ground, it is buried in the ground with a depth of 1 meter. So in 1 meter depth they are all buried. All pipes are uninsulated, so there is no insulation of the pipe. What else we need to require? We need to know how much is the heat transfer coefficient. So we need to assume that they are inner and outer heat transfer coefficient, and the pipe wall is in heat transfer estimation. To calculate the heat transfer coefficient, we need to estimate the heat transfer at a temperature of 5 degrees Celsius for all branches of the pipes. Okay, And with this schedule number, you can see here with the schedule 40, we need to select the diameter 76.2 millimeter for branch 1, and similarly we have different diameters for different branches based on schedule 40. Okay. What we need to find out is what is the calculate the pressure drop and the heat loss inside each branch. This is what we need to find out. Okay, I hope you understand the question. Let's jump into the Aspen HYSYS, and then we will start with the Aspen HYSYS. Okay, so I will start with the new simulation. And one more thing, that the equation of state is Ping-Robinson in this case, so we need to add the components first. So the component when we need to add is from methane to normal hexane, from methane to normal hexane. All these components are same like this. We add those components. Then we have what you call the hypothetical component, C7 plus friction. I will add that one, hypothetical. Similarly, we need to add hypothetical one component. We need to select new hypo. In this hypo, I can call this one C7 plus friction. And what information we have for the hypothetical component? The molecular weight, which is 122, and also the liquid density in pound per feet cube. Either you can go back to the unit and change the unit, or you will just use the unit conversion here. Okay, so the density that we have is 47.45. we change that one here from pound per feet cube. Okay, it will automatically change the density and show up here. This is the two information that we know. The rest of the information we need to let the Aspen HYSYS to estimate. So we click on estimate unknowns. The remaining component will be estimated. We need to add this component here. So add this component here. Now what we need to do, we need to add a few more components: nitrogen, carbon dioxide, and hydrogen sulfide. So nitrogen we need to add. Then we have carbon dioxide. Okay, carbon dioxide. Okay, this one. And finally we have hydrogen sulfide, H2S. This one. Okay, so we have all these components along with the hypothetical component is added. Finally we go to the fluid package, and we need to select the fluid package that will be Ping-Robinson equation of state. Okay, so we're done in the properties section. Now we go to the simulation tab, where we can add all those pipes. Okay, right, so we open up, we need to add what you call the material stream. The material stream that we need to add here first, one by one. So we select one material stream. We can click and add here, double click this one. I can call this material stream gas well 1. Okay, the temperature for this stream is mentioned in the information that I show you before, so we can use that information. So let me find out where is the information. Okay, this one. So the temperature for this one is 40 degrees Celsius. I can use this temperature. Temperature is 40 degrees Celsius. The pressure is 4135 kilopascal. 4135 kilopascal, and finally we have the mole flow rate is 425 kg mole per hour. 425 kg mole per hour. Okay, so that is done. Now we need to add the composition. So composition we have is in terms of sorry. So methane is 0.6230. I wrote down in the page, so I just use that information from there. Okay, so 0.0163, then 0.0043, normal butane is 0.0082, isopentane is 0.0042, 0.0040, normal hexane is 0.0066, C7 plus is 0.0099, nitrogen is 0.0055, we don't have water. What else? Carbon dioxide is, sorry, I think I missed something. N-hexane is 0.0066, C7 plus is 0.0099, nitrogen is 0.0055, sorry, carbon dioxide is 0.0225, and hydrogen sulfide is 0.0154. That's, I think, yeah, that's all about it. Now this is gas stream, gas valve 1. Similarly, we need to add other gas valves, gas valve 2, gas valve 3, and gas valve 4. So what we need to do, we need to create another stream. This is gas valve 2, gas valve 3, and gas valve 4, because we have 4 wells. Okay, so I will go down, I'll go inside, change this one to gas valve 2. Let me change the name first, and then this one is gas valve 3, and this one is called gas valve 4. Okay, now we need to go to gas valve 2. The pressure temperature conditions of gas valve 2 is 45 temperature. 45 temperature, the pressure is 3450 kilopascal, sorry, 3450 kilopascal. Similarly, 375 is the flow rate, 375. Regarding the composition, since it is we are assuming that all the composition of the wells are same, so either we can key in the information manually, or we can just go to define from other streams. So now we already know that we already defined stream 1, the composition. Okay, so what we need to do, we need to take the composition from this stream well into stream 2, and also take the composition from stream 2 to 3 and 3 to 4, like this. Okay, so the way we can do this easily is we click on this button, define from other stream. This window will be open. So from where we can collect the information, we need to collect the information from gas well 1. What information we need to collect from gas well 1? We don't need temperature, we don't need pressure, don't need correlations, don't need cost, don't need flow. What we need only is the composition, and then we click on OK. So stream well 2 will be defined. Similarly, we go to 3. For 3, the temperature what we have is I think we can take okay, so for stream valve 2 we have similar information. For stream valve 3 we have 45, 575, 45 and 575. We don't know the pressure exactly. What we want to know from here, define from other stream, we can take the information of composition, and what else we need? We need the information of pressure, so we need information of pressure from this stream, and we click on OK. That is done. Similarly, for gas well 4, the pressure is 30, the temperature is 35, and the flow rate is 545. We don't know the pressure and the composition, which we can take it from stream well 3. Okay, so we need pressure and composition from this stream. We click OK. That is also defined. So we have 4 different wells that is defined here. Now we need to add pipe segment. So if you look at on your model palette, we need to find out the pipe. We go to the pipe and hydraulics, and this is the one which we need, pipe segment. We click on pipe segment and we can put it here. Okay, so this pipe segment, we can call this pipe segment branch 1. Double click and open. You can call this one branch 1, just like we follow the flow sheets. So the topographic information that is shown, given to us here, this information we are following branch 1. Okay, so this one we can call it, we can take it from gas well 1. The outlet of this one is B dash out. You can give them any other name also, but I'm just giving this name to this stream. Okay, now we need to click on some, we need to give them some information. Here they are asking there is no segment added, means like either it is one segment or it is multiple segments. We need to add the segments. The way we can add the segment is we can go to the rating tab, and if you look at here, we have a few options mentioned here. We need to add a segment. Add a segment is also known as append segment. So we click on append segment. So if you look at your segments, you have according to your flow sheet, you have 1, 2, 3 segments. Okay, so basically you need to add 3 segments. So you can call this one segment number 1. For segment number 1, we have the length which is given to us. If you go to your slides, we are given the length here. Okay, the elevation for segment 1, this information for segment 1, this information for segment number 2. So let's first fill the segment number 1 information. The length is 150 in meters. Similarly, the elevation change that we have is 6 meters. And then we need to click on view segment, because we need to give the diameter of the, to the segment. Okay, so we have not the actual pipe, we have the schedule 40, and the type of schedule 40 we have for this one is 76 millimeter. So let me find out 76 millimeters, which is somewhere, we can call this one 80 millimeters. Okay, something like this. This is how you can define the nominal diameter, and it is mild steel. Make sure it is mild steel. This has to be 76. We don't have the 70, so we can get close to it, which is 80 millimeter. Okay, then after providing this information, we need to close this one. Okay, so once it is done, we need to add another segment. Since we have 3 segments, this segment have a length of 125 meter, And what else they have? Elevation change is minus 8.5. So elevation change is minus 8.5 millimeter. You need to click on the view segment, and also similarly here we need to give them the schedule 40, and we need to provide the nominal diameter of let's say 80. Same. Okay, we need to close this one. Similarly, we need to add another segment because they are based on 3 segments according to this figure: one segment, second segment, and third segment. So based on this one, we need to add a third segment. For third segment, we have the length is 100 meter. We have the elevation, change in elevation 0.55 5 meter, and then we need to go to the view segment tab. We need to click on the schedule 40, and similarly for this one also we need to go for 80 millimeter nominal diameter. Okay, once it is done, if you look at here on your screen, you need to give some information regarding the heat transfer, and we have this heat transfer information which is shown in this particular slide, this one. Okay, this information we need to add here. So what we need to click, we need to add, we need to click on the heat transfer. Okay, once we click on the heat transfer, we can go one by one also. Let's say if you want to go here, go to rating, go to heat transfer, overall heat transfer coefficient. Then we need to add, we need to estimate. I think, let me check with this. Not estimated, yes, this one. Estimate heat transfer coefficient. For estimate heat transfer coefficient, we need to use global. We need to provide the temperature to calculate the heat transfer coefficient, and also we need to include the pipe wall. Include the inner heat transfer coefficient. We are removing the insulation because according to the question we don't have any insulation, uninsulated. Okay, so we remove the insulation part. We need to include the outer heat transfer coefficients. Once you provide this information, you can see your segment is now calculated. Okay, similarly we need to add for another segment. For, let me zoom out. I think I give them some space. Okay, here. So this segment, I can call this one, you can call this one branch 2. Is it branch 2? Let me check again. Yeah, you can call this one branch 2. This one is called branch 2. It will take it from gas well 2 and will take it out, B2 out, and it requires energy stream, which I can call this one B2Q. Okay, you can define with any other name also, but I just give them these names. Similarly, you need to go to rating, and if you look at the figure, it is only one segment, right? So we can click on the sizing, we can click on append and append the segment. Then we can define the length 200 meter, and we have the elevation change which is 23 meter. And we need to click on view segment. We need to provide the schedule number 40 and the nominal diameter, which is let's say we can define this one 100 millimeter. Okay, that is the nominal diameter. And now we can give them a heat transfer coefficient, and it is estimated heat transfer coefficient, global. The temperature, this one is 5 degrees Celsius. What else we need? We need to include the walls, include the inner heat transfer coefficient and outer heat transfer coefficient, and we are not marking or checking the include insulation part because it is not insulated. We leave the rest of the information same, we don't need to change. This one is done. So we done with 2 branches. Now let's talk about so we're done with this one. Now we need to add another one, which is this one, 1, 2 and 3, which is called well C. Okay, so I can call this one well coming from well 3 or well C, whatever you can call this one. Right, again you need to add this one. Click here, double click and open. The inlet for this one is coming from where it is coming from. If you look at here, this one is coming from well 3, so it is coming from well 3. The outlet, you can define outlet out 3, Q out 3. Then you need to click on the rating, and since it is 3 segments, we need to add 3 segments. The first segment is 160 meter in length with elevation change of 12.50. Click on the view segment. This one has a schedule, I think similar schedule you can use. Let's check it here. Yes, branch 2, branch 3. Yeah, we have 40 with 76.2. So schedule 40 with a nominal diameter of, let's say 80. Okay. Similarly, we add the segment. Call this one 100 meter in length, and minus 14 is the elevation change. Click on view segment, click on schedule 40, and similarly select the third one. So later, first we need to this one.
I will carry
this
you
one.
home. When you got nowhere to go, I need you to know I will carry you home. Carry you home.
Right click and open this one. The inlet for this will be given out. Let me count this one. Just let me count it as so now we need to add the segment. We need to click on it. There's only one segment. If accidentally you have done some mistake, then it will close. So segment underscore simulation. I will call this one name of segment underscore simulation. Right, now we need to add another junction. I can call this junction 2, and input is before out, and also B3 out, which we don't have it here, so I can call this one. This one input, and the input for this one. Okay, so this is basically this one is supposed to go inside, and we right, now we need to proceed further. Add it is 90. Yeah, 90 will work. And even for pipe 2, again 90. Okay, you need to do a little bit modification sometimes because the pressure drop is a problem here. Okay. Right, so we're done with branch 6, which is sorted here. Branch 6. Now we need to add a junction 3. This one here. Add junction 3. I will add junction 3. So here. Up junction 3. B5 out and also B6 out, and this one we called as G3 out. And parameters we need to select equalize on. Have something like this. The last branch, you can call this one branch 7. Branch. The inlet to this branch will be G3 out, E7 out. Minus 13 is the elevation, the schedule of 40, and the nominal diameter of something 152. You can call it 150. The heat transfer coefficient again is estimated at 5 degrees Celsius, including the wall, including the heat transfer and outer heat transfer. Done. Okay, so we're done with this one. Then we need to see what is the temperature measurement for it here, and also we need to see junction 3. Junction 3, what is the Celsius, pressure is 21, to 7 kilopascal and water flow rate is 11 to temperature more. This is what we need to find out at the end. What is the pressure, what is the temperature, and what is the water flow rate, because we are getting the this flow rate from different locations. So then we need to find out what is the temperature, pressure, and flow rate of the final location, which this one we need to send into the plant, which is here, the gas plant. You can call this one gas plant also if you want. Okay, so this one is going further to a gas plant where you can have right for the processing. So if you read correctly, this is how the simulation looks like. So the idea of the simulation is to take the flow, take the gases from the gas lines, send them through pipeline to the location where the plant is located, where you can process them. So the idea is to use different pipeline with different segments, and the idea is that you have different junctions and different branches, different segments, just combining at different junctions, different segments combining at different junctions, different segment combining at different junction, and at the end combined information will be shown up here, which is you need to know. Okay, so I hope you understand today's simulation, this topic. If you have if you want to know any if you have any questions, you can feel free to ask. Okay, thank you very much for listening to me. Take care and bye.